Welcome to Algebra 2, Unit 3, Lesson 1, Part 4. We are going to spend just 2 more classes in this particular lesson. So we're really taking our time with factoring. Now you'll notice that the title of this lesson is The End of Factoring for Now. And this is how popular factoring is. He's coming to join us. So there he is. All right. So I'll see if I can convince him to keep going. There it goes. Also, I believe the blue angels keep flying over my apartment. So if you hear something that sounds like planes in the background, it probably is. Now, we are going to put a pause on factoring for now. There are a couple more things that we need to cover with factoring, but we are going to cover those in a later unit. So this lesson will wrap up everything that you need to know about factoring for the time being. And it's really almost everything you would need to know about factoring. There's just a couple of straggling topics that are yet to come. So for the warm-up, this is what the warm-up is that we would be doing in class. If you're watching this to make up class, I know I've said this before, make sure that you are pausing the video and you're participating in all the pieces of the class and not just trying to like zoom through the video to get, to the homework assignment. I promise the video is not going to be that long. It is only 7 slides. So use what you know of multiplication and guess and check to solve the equation below. So we have x plus 3 in parentheses, multiplying x plus 4 in parentheses, and then the product of that is equal to 0. So it's a little bit different from what we've been doing in that now we have this equal sign there. So you know that you have multiplication there. You have some like adding in the parentheses and the parentheses are being multiplied. Pause the video and try to figure out what x could be equal. I will give you this one hint. There is more than one answer to the problem. So go ahead, pause the video and see what you can come up with. Make sure you're making some notes on your own. Okay, I hope you did indeed take the time to do that. So what I hope that as you kind of tinkered with this, you might have jumped right to the guess and check, and that's okay. Okay, if you're thinking, I don't know what she's referring to about that multiplication, that addition stuff, I'll just plug in a number and see what happens. So let's say you plugged in the number 1, which might be a good place to start, and just see what happens. See what happens when you plug in a 1. So you might have 1 plus 3 times 1 plus 4, and that would be equal to 4 times 5, which is clearly not 0, okay? So 20 equals 0 is a false statement, so 1 doesn't work. And you might do that a couple of times before you think, well, in order for that to be equal to 0, I would need to have one of the two numbers be a 0. Okay, so that's what we would need to have. And it might take you a couple of times, like just guessing some answers and seeing what happened. And then you start to think back, okay, if I want the end result to be 0, then one of those parentheses must be 0. And so you could look at it and say, well, if I had a -3, what would happen? Okay, so let's go ahead and check out the -3. So if you plug in -3 for x, then you would have 0 right there in the left parenthesis. This would be 1, and 0 times 1 is 0. And so that checks. And then you might look at the other parenthesis and say, well, wait a minute, I could make it that one 0. If that one was 0, we would use a -4. And so you would plug in, sorry, that should be a plus sign, a -4. And then this would be -1, but now the other one would be 0, and you would end up with -4 working also. And it might take you a little bit of time to get there with it. Now, the question that we're driving at, this is actually going to lead into our next lesson. So this warm-up is kind of getting you thinking about factors and why we would spend 4 class periods working on factoring. Like, it must be important, it must do something. And it does. So the next question is could you do the same thing if x plus 3 times x plus 4 equaled 60 instead of 0? And the follow-up there is, what makes the 0 unique? So if you had a 60 right here, would you be able to work the same thing? Okay, would you be able to figure out what values you would have for x? And there's not like a super straightforward answer to that. Okay, it's just something that I want you to consider about what makes the 0 unique there. Okay, so moving on from that. Review from last class's warm-up. Last class's warm-up, so if you weren't in class and you haven't watched the previous video, please watch the previous video because it does go through that. And if you were in class last period, you should have your notes and you should have some reflections from the warm-up. This is the sheet that I have. I haven't run it off for copies yet, and my background thing is making it blurry. But in last class's warm-up, we did talk about something called the difference of squares. And I don't want you to just try to memorize vocabulary with no context. Okay, so what we call things and what we name them, there is a reason for it, and it does, make sense. It's grounded in something. So the word difference in mathematics means subtraction. And I use the illustration, even in the last video, I use the illustration of, suppose we wanted to know the difference between your age and my age. What's the difference in our ages? We would subtract. And I think most of you, if I asked you that question and said, okay, what operation did you do? You would say subtraction. So difference means subtraction, to find out how much space there is. Here's my other hand. Space there is between two things. Squares refers to something called perfect squares. Okay, so that we have this expression, difference of squares. Squares refers to something called perfect squares. Perfect squares are a set of numbers. I don't know if you can hear the flames, but that are the integers squared. So for example, 1 squared, which of course means 1 times 1 is 1. 2 squared means 2 times 2, which is 4. 3 squared means 3 times 3, which is 9. And then we could do more. We could do 4 times 4, 5 times 5. This set of numbers right here are what are called the perfect squares. And there's an infinite number of them. You would obviously not be expected to know them all, but they keep going, like 6 squared is 36, 7 squared is 49. You should be able to recognize the perfect squares up through about 100, maybe 12 times 12, which is 144. After that, you would probably only recognize them if you had recently done a problem. So if you recently did a problem with 16 times 16, then you would probably recognize the number, but normally no. Now, other things that might be considered perfect squares could be like x squared or x squared, okay? So you could throw a variable in there as well. We will not be looking at x squared. Like, not today, probably not anytime soon, maybe not ever, I don't know. But all of those things refer to, like, perfect squares are what we would refer to as perfect squares. So we have this expression up here called the difference of squares. And when you hear that, like, you just want to connect it to what it means. It means the subtraction between two of these things that are called perfect squares, okay, or two expressions that are perfect squares, and then the operation would be subtraction. So these types of problems always factor according to a particular pattern. So this right here, let me turn the pointer on, is the difference of two squares. Now here's the difference, okay, is subtraction. And then the two things that are being subtracted are, again, these things called perfect squares. When you factor them, you will always get a plus b times a minus b. And of course, you could write a minus b times a plus b. Okay, those are the same thing. But they factor according to that pattern all the time. And what we were driving at in the last warm-up was to try to help you see that pattern, that when you were using the area model every single time you got an answer to a problem like that you were getting this pattern. Because I could just give you a formula, but if that formula doesn't make any sense to you, if you don't see where it comes from, if you don't see why it's reasonable, probably in about a week, you are going to forget the formula. You're just going to forget it unless you practice it and practice it and practice it. And most of us don't have time to practice it that much. Now, the name for this type of factorization, we say they factor into what are called conjugates, conjugates, conjugates. Super, super, super important concept in math. Okay, I'm going to star it. It's a super important concept in mathematics, this idea of conjugates. And the reason they're important is because when you multiply them on the rectangle, the terms on the diagonals end up canceling out. So just so you could see, here are some examples of factoring by conjugates, or factoring with the formula. So the first example is x squared minus 25. Now, I'm going to do a step here that normally we would leave out, but I do want you to see what that middle piece of the reasoning is. What you might see someone do is they'll take the 25 and they will rewrite it as 5 squared. Now, the reason people do that is to make the problem look like the formula, where you can see that your a value is x and your b value is 5. Okay, which means that when you factor it, you'll have x plus 5, x minus 5. And most of the time, I would not write that. I would just look at that and say, okay, x squared minus 25, that's difference of squares. It's going to factor into conjugates, x plus 5, x minus 5. In fact, my brain doesn't even do that much. Okay, I just factor it. The second one is a little bit harder to look at. So we have 4x squared minus 36. And what you would want to notice about this is that you had 4, which is 2 squared. And then we have the x squared, and then 36 is 6 squared. And then you might do this. Now, we have not reviewed laws of exponents yet, so I'm just gonna like kind of put the brakes on that rewrite there. I just want you to see that it does work with a number out in front of the x squared. Okay, so it does work with a coefficient, and this will factor into 2x plus 6 and 2x minus 6. Now, the last example there, you might look at that and say, hold up, Miss Taylor, 18 and 8 are not perfect squares. This is true. So we go back to that pesky, annoying first step that we have to take all the time, which is look for a GCF. So before you do anything else, you do scan it and you look for a GCF. The only reason that I'm not doing it over here is mostly because I wrote these problems and I know there's no GCF, and then I forgot to go through the step. But you do want to check for that GCF. 18 and 8 are both even numbers, so I know that there is at least a common factor of 2. If there's a bigger one, I always want to get the biggest one, hence the greatest part of greatest common factor. But for now, let's factor out a 2. That's going to leave me with 9x squared minus 4. And then hopefully you recognize that 9 and 4 are perfect squares, and so that's going to factor according to our pattern. We would do 3x because 3 squared would give you the 9, and then we would do plus 2 because 2 squared gives you the 4, and then 3x minus 2. If you cannot see that, I'm going to say it out loud again and give you a chance to write it down. So the 9x squared comes from 3x squared. Okay, so 3 squared gives you the 9 and then the x squared. And so we would have 3x and then the plus, and then 2 squared is equal to 4. So it's 3x plus 2. which is that part right there. And then the other parenthesis will be 3x minus 2. And then, of course, if we're asked to factor, we need to give all of the factors. So that would include the 2 as well. So there are some examples of difference of squares and what the formula is and how the formula looks when you carry it out. So it does work on the area model as well. I don't know why there's a line missing, but I guess I'll have to draw it in because I think my next line is, I think if I hit go, it's going to give me the next slide, not the slide. So the area model will work for this. So we would put 9x squared in the upper left and -1 in the lower right. And then we would do 9 times -1 to get -9. Now we do want to remember it is a -9, but for our factoring purposes, we're just going to look at the 9. We need 1 times 9 and 3 times 3. So it's going to be the 3 and the 3 that work because we need to get them to add up to 0. So just so you can see what's going on there, I might have gone through that a little bit fast. So what we have here is 9x squared plus 0x minus 1. And again, this does go back to the previous warm-up. So if you were in class and didn't do the warm-up, or you rushed through the video and you didn't stop and do that warm-up, please go back and do that warm-up. But we've got the x squared, we don't have any x's at all, and then we have the -1. And so whatever is on our diagonal needs to add up to 0. And so when I start looking at that 9, I know I'm going to use the 3 and the 3. One of them will be positive, one of them will be negative. And then we will factor out, going to the left over here. If I group these two together, the common factor is 3x. And that would make that a 3x up there. 3x times what would give me 3x? Well, that would be a 1. And then down here, 3x times what would give me -3x? That would be -1. And there's my answers, 3x plus 1 and 3x minus 1. And you can see that that does fit the pattern that we covered on the previous slide. So one of the things you can do with math, because math is consistent and because the area model is a representation of what we're doing, we're just using the area of rectangles to be able to visualize it. But when you see a pattern and then you can confirm the pattern, you can exploit the pattern, which means that you can take a shortcut. Just don't take shortcuts that you don't understand. Okay, do not grasp formulas if the formulas don't make sense or you're not sure when or how you should use them. Now, you may also want to opt for the formula. Okay, so looking at this one, we have 36x squared minus 49. I hope you can recognize that 36 is a perfect square, as is 49. 36 is 6 squared and 49 is 7 squared. So when I go to factor this, I will figure, okay, well, what times itself gives me 36? That's 6. And then we have the x. And then we know that one of them is a plus and one of them is a minus. And then what times itself gives me 49? Well, that would be 7. And so we would have 6x plus 7 and 6x minus 7. You could check that if you wanted to by using our area model to multiply it together. Okay, so 36x squared, positive 42x, negative 42x, and negative 49. Okay, so you can see there that, yep, the diagonals would cancel out and you would be left with 36x squared minus 49. So I don't want all that. Shoot. Okay, I don't know why it wasn't letting me erase that, but I guess I'm not going to argue with it. Now, this would be harder with the area model since we'd need to multiply 36 and 49. and we'd end up with a very big number. So if you were trying to do this with the area model, you would have to do 36 times 49. And I think most of you right then and there, you're like, that's going to be huge. So that's why formulas do work, why we do want to be observant and get those shortcuts when we can, because sometimes the mechanics of a particular problem might be pretty awful. Use the method that works for you. So while the right answer is important, and I don't want to make it sound like I don't care whether you get the right answer, because I do, it is more important that you understand, that you're able to demonstrate the concepts at work, that you understand what's working, that you can visualize it. It doesn't do you a lot of good in the long run to get a right answer if you don't understand why that right answer makes sense. So use the method that works for you, and I just wanted you to see that both methods do work and to see what the advantage to using the formula is. So what is left? So classwork, I told you it was going to be a short video, okay? Classwork, homework, and for funsies work, because sometimes there are interesting problems and questions to ask for no other reason other than this might be an interesting question. So for classwork, you are going to log into Desmos, and your goal is to complete 7A and 8A. So that will be 6 problems. And then your homework will be 9A and 10A, which are your homework problems. So you figure by the time you get through with 10A, if there are 3 problems per set, you will have done 30 practice problems. Actually, a little bit more, because I added in 1 for the warm-up last class. If you finish those early, so you get like on a tear with your factoring, you're like, I got this, I want you to consider this problem. How could you use a graph to figure out the values of x for this equation? 2x squared plus 9x minus 5 equals 0. Talk about it with a neighbor. Hop onto Desmos. Okay, so I said try a few things on Desmos and then check your answer. If you know what x is, if you check a value of x, remember you should be getting a true statement. So you could pick a value for x. You could try x equals 1 and see what happens. Okay, but before you start picking x equals 1, x equals 5, whatever you're picking, I want you to at least graph it on Desmos and see if you can make some kind of sense of that 0 and the left-hand side there, and see what you can see. Okay, I'm very curious to see what you come up with. It's risk-free. It is honestly for funsies. Okay, it's just for funsies. Can you figure it out? You do have the knowledge that you need to be able to figure it out. See what you can do with it. No pressure, just for fun, okay? Let me know if you have questions, if you have trouble accessing any of the assignments, and I will do my best to help you out.